Assalamualaikum and hi, my name is Nurul Hafsa binti Sawizi. Today I will present about predictive model for tool wear and burr formation in micromilling of titanium alloy. The team members are Dr. Ti6Al4V, Dr. Zailani, Dr. Nur Aizat and Mr. Muhammad Farizwan. For introduction, micromilling is a manufacturing process used to produce mini-sized components with high precision, high quality surface finish. It involves the use of miniature cutting tools to machine material with decent accuracy. This process is widely utilized in industries such as aerospace, biomedical, electronics, and watchmaking, where micro-sized parts with complex geometries are essential. Here shows the example of micromilling of slot making process and also example of micro components in watchmaking made of titanium alloy. There are three problem statements. The first one is the unpredictable tool life and premature tool failure are a big issues in micromilling. The second one is optimal machining strategies difficult to predict with the existence of burr formation in micromilling. The third one is micromilling cutters have different behavior compared to conventional macro tools. Next, motivation of the project. Excessive tool wear and burr can lead to surface defects and dimensional inaccuracies. Therefore, this research is initiated to develop a prediction model based on tool wear and burr. The outcome from the developed model help to assist manufacturers in terms of scheduled tool replacement or minimizing downtime. The objective of this project is to investigate the tool wear state and burr formation during micromilling of titanium alloy under different cutting parameters. To develop a predictive model based on tool wear and burr response by using RSM. After that, research question. To know how does the tool wear and burr form with the changes of spindle speed, feed rate and depth of cut. And to know how accurate the tool wear and burr response to train their own predictive model. After several previous studies, some research gaps were found. Most of prediction models were based on single or individual signals, either for tool wear or burr formation. Since tool wear and burr are the undesired outcome, it is better for fuse the signals rather than analyzing them separately. There is still limited research on PEC and prediction of titanium alloy at a microscale level, since most of the studies found at conventional or macro scale. There is limited research on RSM in generating predictive models based on tool wear and burr. Most of them are found to predict other responses such as surface roughness, cutting force, acoustic, and vibration. For the methodology, it starts with introduction, followed by literature review. Next is design of experiment with a combination of full factorial and RSM. Next is micromilling experiment under dry condition with various spindle speed, feed rate, and depth of cut. During the experiment, if the experiment can pass in single experiment, it will be proceeded to the next step. But if the experiment cannot pass in single experiment, it need to replace the new tool before proceeding with the next step. After that, tool wear and burr measurement. Tool wear measurement is based on maximum flank wear while BURR measurement is based on BURR width. And then analysis and prediction model development by using ANOVA and RSM via design expert software. Lastly, the validation of the model to see the percentage accuracy of the predictive model. The workpiece material that has been used in this experiment is titanium alloy cutting tool, crisp precision with diameter of 1 mm, machine tool of Akira Seiki 3-axis CNC machine, microscope of TM3000, scanning electron microscope SEM. The cutting parameter that has been used is in the range of 1000 to 10,000 RPM for spindle speed, 50 to 150 mm per minute for feed rate, and 0.10 to 0.20 mm for depth cut. For design of experiment, this table shows the result from design expert software. There are 20 experiments for this project. Next is the result. After the 20 experiments, it is found that the least BURR width is 0.092 with spindle speed of 3000 RPM, feed rate of 50 mm per minute, depth of cut of 0.10 mm. Meanwhile, for tool wear, the minimum tool wear is 0.013 with spindle speed of 5500 RPM, feed rate of 100 mm per minute, and depth of cut of 0.20 mm. This picture shows tool flank wear observation and measurement using scanning electron microscope. This is tool wear contour plot, the smallest predicted tool wear at constant feed rate of 0.0287 mm. Based on RSM results, tool wear measurement range from 0.013 mm to 0.250 mm. This is the tool wear prediction model after using the design expert software. Next, for BURR, the pictures show the BURR width observation and measurement using scanning electron microscope. This is BURR contour plot, smallest predicted BURR at constant spindle speed of 0.0223 mm. This is the BURR prediction model after using the design expert software. For conclusion, by employing RSM and ANOVA through design expert software, a predictive model is developed to optimize machining conditions, minimize tool wear, and BURR width. For tool wear, spindle speed of 5500 RPM, feed rate of 100 mm per minute, and depth of cut of 0.20 mm resulted in the least flank wear of 0.013 mm. A balanced combination of cutting speed, feed rate, and depth of cut helped to reduce tool wear. For BURR formation, spindle speed of 3000 RPM, feed rate of 50 mm per minute, and depth of cut of 0.10 mm resulted in the least BURR width of 0.092 mm. Lower spindle speed, reduced feed rate, and shallow depth of cut contributed to minimizing BURR formation. Next, impact or novelty of project, smart manufacturing and industry 4.0. These models could integrate the machine learning-based tool condition monitoring. Sustainability working on predictive settings could reduce tool wear and BURR formation, therefore minimize material wastage on and rework. Process optimization. The outcomes of this project provide empirical validation of optimal milling conditions that future researchers and practitioners. Data-driven decision making. This project encourages the use of data from machining for precision machining, bridging the gap between traditional and AI-powered manufacturing. This is the project funding by Fundamental Research Grant Scheme and industry collaborator ISES Jiran Berhad. This is the list of references that has been used in this slide. That's all from me. Thank you.